2, class number 2 for college geometry. Today we are going to continue with our discussion of various angles, rules regarding angles, etc., etc., etc. By the end of the day I want to finish up with chapter 2 in the book, and I would also like to give you enough information to do homework number 1. As this is a very light class in terms of attendance, I want to encourage everybody to ask questions. If you have any questions, please feel free to go about doing so. And if I ask questions, I appreciate if people participate when I do ask questions. Okay, so let us go on with what we were discussing last time. And last time we had been discussing pairs of angles. And, excuse me. And we were discussing these two pairs of angles, these two types of angles called complementary angles and supplementary angles. Complementary angles are angles that equal up to a right angle, that equal up to 90 degrees. The most common example is when you have a right angle being something like this. Okay. And this is a right angle, so this is 90 degrees because it's 1/4 of a circle. Let's say you split this up. For example, let's say you have a right angle, and we'll draw it like this, a nice right angle over here. And let's say I put another line over here. Now, let's say I call this angle 1 and this angle 2. If I add up the measure of angle 1 plus the measure of angle 2, what will I get? What will the total be? The total will be 90, that's correct. Because the whole thing, by definition, has to equal 90 because the whole thing is a right angle, and therefore these two angles, angle 1 and angle 2, are complementary. Supplementary is a very similar concept, except supplementary is when the two angles have to equal 180 altogether. The example there is when you're talking about a straight line. So if you're talking about a straight line, and you've got angle 1 and angle 2. Now angle 1 and angle 2 have to equal what altogether? Angle 1 plus angle 2 has to equal altogether 180. Very good. Why is that? Because a straight line is a half a circle, and a half a circle is 180 degrees. So in this case, the two angles are considered supplementary. So whenever you hear the term complementary angles, they have to equal up to 90, and supplementary angles have to equal up to 180. Again, a lot of these are kind of vocabulary terms that will come up over and over again. Now we're going to get away from the world of points and lines and angles, and to the point where they actually build up. Because when you build points and lines and angles, you get shapes. And shapes are known as polygons. Poly from the Greek term meaning many or meaning multiple. Shapes, by definition, have multiple sides. So there are many different types of polygons, and on this slide over here we've got a whole bunch of different types, and they are all based on the number of sides. A circle, of course, doesn't have a specific number of sides. A circle really has kind of an infinite number of sides. A circle goes around so that the points are not there's no corners of a circle. You all essentially know what a circle is. But other types of polygons are based on the number of sides. A 3-sided polygon, you all knew, I'm sure, was a triangle. A 4-sided polygon is a quadrilateral. You might not have heard that term. You might have called it a rectangle or a square. Those are examples of quadrilateral, but anything that has 4 sides is a quadrilateral. For example, this, let's say, well, okay, bad example. This is not a square, and it's not a rectangle. It's really no special type of quadrilateral, but it is a quadrilateral. A pentagon is a 5-sided figure, like the Pentagon in Washington, D.C. Okay, not a very artistic pentagon, but a pentagon nonetheless. The reason why the Pentagon building, the headquarters of the military, is called the Pentagon is because it has 5 sides. It is shaped like a pentagon. If you go on Google Earth or whatever and you look at an aerial view of the Pentagon, you'll see it as a nice regular pentagon, which means that all the sides are equal. It's a very artistic building, but it's a pentagon. A hexagon has 6 sides. A septagon has 7 sides because the month of September used to actually be the 7th, or not because of that, but the sept in I guess Latin is 7. September used to be the 7th month of the year, but in those days there was no such thing as I think there was no January or February. I think the year started with March. But anyway, September was the 7th month, October was the 8th month, and you have septagon and octagon. You also have more. You've got nonagon, which is 9 sides. You've got decagon, which is 10 sides. The key other point that I have over here on this slide, of course, is that when you add up the number of degrees in the interior in any of these polygons, essentially it's 180 times the number of sides minus 2. So, for example, a triangle, I think we discussed this last time, the three angles of a triangle, angle 1, angle 2, and angle 3, have to equal up to what? Angle 1 plus angle 2 plus angle 3 has to equal up to 180 degrees. And the reason is because a triangle's got 3 sides. Subtract 2, multiply by 180, and you got 1 times 180, which is 180. A quadrilateral has to have 360 degrees. Angle 1 plus angle 2 plus angle 3 plus angle 4. It doesn't matter what kind of a quadrilateral. Could be a rectangle, could be a rhombus, could be a square, could be a trapezoid, all types of quadrilaterals. All of these 4 have to equal 360 degrees total. And for every side you add, you have to add in 180 degrees. So for example, in this pentagon over here, if you have 5 angles, and of course if you have 5 sides, it also means you have to have 5 angles. It also means you have to have 5 junctions, which are angles. If you add angle 1 plus angle 2 plus angle 3 plus angle 4 plus angle 5, you're going to get 540 degrees. A stop sign, for example, if you add up a stop sign, well, there you have a stop sign. It's an octagon, right? Or is it a hexagon? No, it's a hexagon. What am I talking about? A stop sign is a hexagon, I think. Why am I drawing a blank? Now I'm going to have to Google stop sign because for some reason I'm drawing a blank on an octagon. Thank you very much. Okay, but I still have to Google stop sign because I am. Yes, that is an octagon. All right. All right. So if you added up all the angles in an octagon, and a stop sign, that would be 1,080 degrees. That, by the way, a stop sign is what's called a regular octagon. A regular polygon means all the angles are the same. So an octagon has 1,080 degrees, and all 8 angles are the same. So if you want to know what each angle of a stop sign is, it would be 1080 divided by 8 angles, and that would be 135 degrees. So if you take out your protractor, if you want to actually go outside, anybody want to actually do this? Take out your protractor, which you can measure degrees, and go out and find your nearest stop sign and start measuring the angles. Either you'll get arrested or you'll be able to tell people very interesting information because people will come over to you and say, you know, what are you doing? And you say, I'm measuring the number of degrees in each angle of this stop sign just to make sure that it's 135 degrees for each angle. And if it's not 135 degrees, then you can call the state and tell them that they need a new stop sign because stop signs are supposed to be regular octagons. Okay. All right. And if you try that, let me know. I want to be there and see what happens. Okay. Then, now that we are going to really not so much focus on pentagons and octagons and hexagons and stuff like that, we're really going to focus on triangles and quadrilaterals. And there are many different types of triangles. An equilateral triangle means a triangle that has 3 equal sides. Now, the thing about a triangle with 3 equal sides, and this is not exactly an equilateral triangle, but it's pretty cold. No, it's okay. It's not really a cold anymore. It's just kind of you know, it gets the lungs get irritated, and once the lungs get irritated, it takes weeks for it to go away. But I really don't have much of a cold anymore. It's just, you know, irritated lungs, if you will. But it'll go away eventually. All right. So let's say we've got an equilateral triangle over here, which means this equals this equals this. That also means the angles have to be equal. Generally speaking, if the sides are equal, then by definition the angles have to be equal also. Which means in an equilateral triangle, how many degrees are each angle? Well, it has to be 180 altogether, and therefore each one has to be 60 degrees, exactly. Then there is something called an isosceles triangle. An isosceles triangle, I'll abbreviate it ISOS, means you have two equal sides. Let's draw this relatively straight if we can. If these two sides are equal, this with that, that means two of the sides are equal, but the third side is not. That also means, by the way, that the base angles are equal to each other. So this angle is equal to that angle. Angle 1 is equal to angle 2. Now, angle 3 is not equal to 1 or 2, but the base angles of an isosceles triangle have to be equal. You'll see that a lot. When sides are equal, it usually follows that angles have to be equal also. A scalene triangle, on the other hand, simply has no equal sides, basically a random triangle where none of the sides are equal to each other. That's just a plain old run-of-the-mill scalene triangle. An acute triangle is any triangle where all three angles are less than 90 degrees. Remember, an acute angle is less than 90 degrees. Now, some of these could be both. For example, an equilateral triangle, by definition, has to be an acute triangle. Why does an equilateral triangle have to be acute? Well, equilateral triangles have to be 60, 60, and 60. Exactly. All of those are acute. Acute angles, as you hopefully recall from last time, are any angles that are lower than 90 degrees. If it's a right angle, well, then it's higher than it's 90 degrees. Or if it's an obtuse angle, which is higher than 90 also, that's fine, but it cannot be an equilateral triangle. Now, okay. So, then there is an obtuse or a right triangle. A right triangle is a triangle with a right angle in it. Of course, there can only be one right angle in a triangle, because the right angle is 90 degrees, which means the other two have to equal up to what? Angle 1 and angle 2 have to equal up to 90 also, because the whole triangle has to equal up to 180 altogether, and the right angle already consumed 90 of them. Therefore, the other two, we can say, for example, that angle 1 and angle 2 are what? What word would we use to describe the relationship of angle 1 and angle 2? Well, how about complementary? Very good. Because they have to equal 90 degrees altogether. Then you can have an obtuse triangle. An obtuse triangle is a triangle that has an obtuse angle. Of course, once again, you can only have one of them. Let's say you've got a triangle that looks like this. Well, this is an obtuse triangle because this angle is bigger than 90. This angle is between 90 and 180 degrees. That, of course, means the other two angles are going to be very small, because that means the other two angles are going to combined add up to less than 90. Can you have an isosceles right triangle? Can anybody tell me? Does that work? Can you have an isosceles right triangle? The answer to that is yes, you can. Isosceles means you can have two sides that are equal, and the third, so let's say these two are equal. Okay, let's say this is equal to this. That means this is an isosceles right triangle. Can you have an isosceles obtuse triangle? Again, the answer is absolutely yes, you can. It doesn't have to be, but it can. Let's assume these two sides are equal, and the third side forms an obtuse angle. Can you have an equilateral right triangle? No, can't do that. Equilateral means all three sides have to be equal. In a right triangle, does one of the sides have to be bigger than the other sides? The answer to that is yes. The side opposite the right angle has to be the biggest one. This one over here, the slanty one, the one going down the right side, exactly. That has a special name, which I want you to remember because it's a very important word in this course. That is called the hypotenuse. The hypotenuse is the line or the side of a right triangle that is opposite the right angle. Can you have an equilateral obtuse triangle? No, for the same reason. That's right. If you look at an obtuse triangle, the one opposite the obtuse angle is going to be the longer side, usually by far. So in a right triangle, the hypotenuse has to be the longest side. You can have a right triangle that's also an isosceles triangle, like this one. You can have an obtuse triangle that's also an isosceles, like this one. But you cannot have an equilateral of either one. Okay, those are some examples of various triangles, and we're going to come back to them. And every time we deal with one of these, I'm going to redefine it. So hopefully you remember this, but if you don't, that's okay too. Now let's take a look at certain types of quadrilaterals. Quadrilateral, remember, means a four-sided figure. And any four-sided figure is a quadrilateral, but there is a special kind of quadrilateral that is dealt with very often called a parallelogram. You know, that's not drawn very well. I'm going to try to draw it a little bit better. Okay, still not great, but not terrible. Okay, so we've got this here. This shape is going to be called a parallelogram. A parallelogram has really 5 rules. In fact, I'm going to go to the next slide over here, which tells you the rules of the parallelogram. Every parallelogram has these rules. Number 1, opposite sides are parallel. Let's say this corner is called A, this point is B, this point is C, this point is D. First of all, opposite sides are parallel, so this line is parallel to this line. AB is parallel to CD. Make sense? That's why it's called a parallelogram. BC is also parallel to AD. I'm making 2 ticks to indicate that the ones with 2 ticks are parallel to the ones with 2 ticks, and the ones with 1 arrow, really arrows, and the ones with 1 arrow are parallel to the ones with 1 arrow. Now, also, the second rule is that opposite sides are equal. So who can give me 2 sides that are equal? You got 2 choices, really. There are 2 pairs. AB and CD are equal. Good. AB and CD are equal. And BC and AD are equal. Excellent. Number 3, opposite angles are equal, which means angle A, or BAD, and angle C, or DCB, are equal. And it also means that angle D, I'm going to use 2 of these thingamajigs, are equal to angle B. Okay, that's 3 rules. Number 4, 4th rule, consecutive angles are supplementary. Supplementary means they add up to how many? Angle A plus angle B equal 180 degrees. Good. And also, angle C plus angle D equals 180. Think about it. It's perfectly logical if you think about rule 3. How many degrees does the whole parallelogram have to equal, all 4 angles? They have to equal 180, right? Well, if the opposite ones have to be equal to each other, that means each half have to be half the total. So A plus B is 180, B plus C is 180, C plus D is 180, A plus D is 180. All of any 2 consecutive angles are going to be supplementary, which means they have to equal up to 180. And I know this is a lot to memorize, but hopefully the fact that it's logical and that it makes sense will help. And the last rule for a parallelogram that I want you to remember is that diagonals, and okay, I'm going to have to try to draw this with a straight edge, otherwise it's not really going to look bad. All right. Yikes. No, that didn't work. Okay. You know what, never mind. I can't really use a straight edge with this thing. Alright, this is one diagonal, and this is another diagonal. Alright, they don't look great, but I guess hopefully they look okay. Diagonals means lines that crisscross from one corner to another. They bisect each other, which means this half of this segment's equal to that half, and this half is equal to that half. Where they meet in the middle, that slices each one of them in half. Those are the 5 rules of a parallelogram. And there are 3 subtypes of parallelograms that I would like you to remember what they are. There are 3 subtypes over here. Number 1 is a rectangle. You all know what a rectangle is just from general life. Just remember when you were 3 years old and you were playing with your blocks and you got one block that was a rectangle? Well, scientifically, or mathematically really, what is a rectangle? All a rectangle is, it's a parallelogram with a right angle. Now, if it has one right angle, by definition it has to have 4 right angles. And you'll see why. If you have a let's assume I really wish I had a little bit better artistry over here, but this will have to do. Let's say we've got a parallelogram here. If this is a right angle, well, think about it. If this is a right angle, then if A is a right angle, then what does B have to be? How many degrees does B have to be? 90, because remember, their consecutive angles are supplementary. So if A is 90 and A plus B have to equal 180, so B has to be 90 also. What is C? Well, C, you can figure out is 90 either because it's equal to A, it's opposite A, or because it's supplementary with B. Either way, C has to be 90. And D, of course, there are lots of different ways you can tell that D has to be 90. Either you could tell that D has to be 90 because it's supplementary with C, or because it's supplementary with A, or because it's equal to B, or because the entire total has to equal up to 360 and the other 3 angles combined are 270. Either way, B is going to be a right angle. This is now a rectangle. Now, what special rule does a rectangle have over and above the parallelogram? Well, the angles are all right angles. A parallelogram with 4 right angles, or 1 right angle really, and therefore by definition 4 right angles, is inherently considered a rectangle. Well, square is really a type of rectangle. We're going to see what a square is in a couple of minutes. But rectangles are important because rectangles, when we get to areas, rectangles, and we get to the square, the square yardage or the square footage in a rectangle, there's a formula that works for a rectangle and doesn't work for a regular parallelogram. So that's really why it's important. The next type of parallelogram that I want to quickly go over is the rhombus. A rhombus is a parallelogram where all 4 sides are equal to each other. So let's say this is a parallelogram, and this side is equal to this side. Well, we already know that opposite sides are equal, so basically it means all 4 sides are equal. The rhombus has all the same rules as a parallelogram, but it also has one additional rule, and that is that diagonals are not only bisect each other, but diagonals are perpendicular to each other. Which means you see these 2 blue lines? They form at a right angle. Where they crisscross, it's a right angle. Now, it may not look like that on my drawing because my drawing isn't very good, but if you take out a ruler or a straight edge and you draw a rhombus, let's say each side is 2 inches long, and then you draw 2 diagonals from the corners to each other, you'll see that they crisscross at a right angle. You'll see that they cross literally perpendicular to each other. So that's the rule for a rhombus. And I know I'm doing a lot of these rules. We're going to revisit these rules as we move along. The last special type of parallelogram is the square. The square, you all know what a square is? Well, a square is really a combination of a rhombus and a rectangle. A square has sides that are equal to each other, and it also has a right angle, and it's also a parallelogram, which means all. And I can tell you something about a square. A square is a very artistic shape. Everything is equal. The angles are all equal to each other. The diagonals are equal to each other. The diagonals are perpendicular. The angles that are made by the diagonals are going to be equal to each other. Everything you can possibly imagine in a square is going to be equal to each other. If I make 2 diagonals, not only are the diagonals equal to each other, and not only are the diagonals perpendicular, but this angle is equal to all these angles made by the diagonals are equal to each other. Pretty much everything is equal. So that's a square. Those are the 3 basic types of subtypes of parallelograms. They are all parallelograms. They all observe the 5 rules of the parallelograms. If you notice the rule that opposite sides are parallel, opposite sides are equal, diagonals bisect each other, consecutive angles are supplementary, opposite angles are equal. All of those rules apply to all 3 of these subtypes, to a rectangle, rhombus, and a square. And finally, our last type, did we do the trapezoid? Where's the trapezoid? Yeah, okay, before we go on to the next thing over here, I want to establish a trapezoid. A trapezoid is a quadrilateral where only one pair of sides are parallel. This side is parallel to this side, but the other 2 are not. I don't know, you ever play Tetris? If you're under, like, probably 25 years old, you probably have no idea what Tetris is. But for us geezers who remember back in the old days, Tetris was this game where shapes would fall down from the sky and you'd have to manipulate them and slide them in and get whole lines, etc. Oh, really? Huh. I haven't seen Tetris in a long time. Oh, well. Interesting. All right. I guess they still have it floating around somewhere. So Tetris used to be the most sophisticated game. No, I'm kidding. Okay. So it is. As we go to the formulas, we're going to learn about the formulas to figure out the areas of each of these, etc., etc. Okay. Let's take a look at some angle measure rules over here. See this slide over here in the left-hand corner? We've got 2 lines that crisscross. We've got angle A, angle B, angle C, and angle D. First of all, A and B, what is the relationship between, well, it says in the slide, but why are A and B supplementary? Who can articulate why A and B are supplementary? Okay, they have to equal 180 because it's a straight line, right? And a straight line, by definition, has to be 180 degrees altogether. Good. Now, opposite angles are when 2 lines crisscross each other, when 2 straight lines crisscross each other, opposite angles are equal. They're also called sometimes vertical angles. A and C are equal, and B and D are equal. Those are, again, vertical angles. So A and B are supplementary, D and C are supplementary, A and D are supplementary, B and C are supplementary, C and A are equal, and D and B are equal. Simple enough? Hopefully. Okay, good. All right. How do we name polygons? As we move along throughout this course, I'm going to quickly name angles as we move along. I'm going to draw you a diagram and say, what is angle ABC? So we need to get the naming conventions. Conventions for angles are very simple. Angles are named by the 3 points. The point in the middle is the point at which the angle meets, and the other 2 are points on the lines that make up the angle. For example, if this is point A, and this is point B, and this is point C, how would I name this angle? Let's say this is D. I would call this angle ABC. Or, by the way, I could also equally call it angle CBA. Either one is correct, as long as we have B in the middle. Now, in this case, I could also just call it angle B because there's no other possible angle B that there could be. But sometimes, if you have situations where it could get a little confusing, if this is angle B, and this is angle D, and this is point D. Let's say this is point B, this is point A, and this is point C. Well, I can't just say angle B, because there are 2 different possibilities for angle B. If I were talking about this angle, I'd name it angle CBA, or ABC. What about this angle? What about the one on the right side? What would I call that? Good. Angle ABD, or angle DBA. Polygons, in other words, shapes, named by all of the points that make up shape. In the example at the bottom of the slide, well, that is simply rectangle ABCD. So if I start off with a point that says rectangle ABCD, that means that that shape is a rectangle. Simple enough. Okay, let's move on to three-dimensional objects. Three-dimensional, and we're going to come back in many classes on two-dimensional objects, so there'll be plenty of time for that as we move along. Three-dimensional objects, on the other hand, also have similar rules to two-dimensional objects. They are a little bit more complex. As we move along, when it comes to three-dimensional objects, okay, let me take a step back for a second. When I ask you how long a line is, what measurements are you going to give me? Like, what is the unit that you're going to use to describe how long a line is? What are some examples of units that you could use? And there are many examples. There are inches, okay? You can use feet, you can use meters, you could use miles, you could use kilometers, you could use whatever you like. Those are all one-dimensional units of length. If I tell you you have to drive 50 miles to get to, to get to the party, or whatever it is, that is a unit of length. 50 miles in a particular direction. You have to throw the ball 300 feet in order to get somebody else to catch it. You have to hit the golf ball 250 feet in order to get it onto the fairway. Whatever it is, that is a one-dimensional unit. When you're talking about a two-dimensional unit, what's the unit you use in that case? How big is the house? How big is the yard? Yeah, exactly. You could use square feet or square meters or square miles. How big is Rhode Island? It's about 1,100 square miles. How big is, New York? About 50,000 square miles. So yeah, those are, a square mile is two-dimension. That means it's the length by the width. If I say this room is 300 square feet, that means if you take the length and you multiply it by the width, you're going to get 300. How about three-dimensional? How about three dimensions? Well, with three dimensions, instead of using square feet, you use something called cubic feet. Here you might not have heard it, because this is a little bit less, less often used. We may have other cube units. For example, when you buy a bottle of soda or something like that, what's the unit there? What's the unit that soda is I guess in some parts of the country they call it pop, but whatever you call it, usually in liters, right? You know what a liter is actually? A liter is a cubic decimeter. A decimeter is 1/10 of a meter. It's about let's see, a decimeter is probably about 4 inches, a little less than 4 inches. So imagine taking 4 inches by 4 inches by 4 inches. That's approximately 1 liter. It is a three-dimensional object. It's a cubic decimeter. A milliliter is also the same thing as a cubic centimeter, which is a centimeter by a centimeter by a centimeter. Centimeter is about 4/10 of an inch or so. So that's a centimeter by a centimeter by a centimeter is a milliliter. 1,000 of those is a liter, which also happens to be a cubic decimeter. A cubic meter would be 100 liters. That would be obviously a lot more. These are three-dimensional areas, exactly, and this is length by width by height. The room I'm standing in now, I'm going to hazard a guess, is something like maybe 250 square feet, let's just say. Now, so it's 250 square feet. Well, let me count the tiles. Let's see, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That way, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So, sorry. Okay. All right. Okay. Yeah. So about 270 square feet. I'm going to estimate about 270 square feet is the room that I'm standing in right now. Now, that is a two-dimensional measurement, square feet. What if I wanted to measure cubic feet? I wanted to measure how much volume is there. Well, then I'd estimate how high is the ceiling. And I'm going to estimate the ceiling is something like, I don't know, maybe 7 feet. Let's just say 7 feet. So I'm going to multiply that by 7 feet. So that's 1,890 cubic feet. So this room is approximately 1,890 cubic feet, which means if I were to measure out, let's say, how much water would it take to fill up this entire room, I would take maybe a foot by a foot by a foot of water, a box that's a foot by a foot by a foot. It would take 1,890 of them to fill up this room. Or maybe it's 7.5 feet. I don't think it's 8 feet. It's probably maybe 7.5 feet. But the point is that the cubic feet obviously are going to be the numbers are going to be a lot higher because you're talking about 3 dimensions rather than just 2. Okay, so that's what we're talking about, 3-dimensional objects. Let's take a look at some examples of 3-dimensional objects that you see on the slide over here. First of all, we've got a triangular prism. Notice that this triangular prism is not a total triangle. It's kind of like a tent. It's got a rectangular bottom. See the bottom? The bottom of that triangular prism is actually rectangular, but it goes up on either side in triangles. Really, you've got 2 triangles on the side, and then you've got... How many rectangles do you see over there? I know this sounds like we're playing a kid's game, but in that triangular prism, yeah, that's right, 3 rectangles. 1 rectangle on the bottom, and 1 rectangle on each side. On the side facing us and the side going away from us, and 2 triangles. So really the surface area of that triangular prism is actually 4 rectangles and 3 rectangles and 2 triangles. Then you got the pyramid. Pyramid's another example of a 3-dimensional object where you've got one either square or rectangle on the bottom, and everything moves up to a certain point. The base is a quadrilateral at the bottom, and they all rise to a particular point. And then you've got these polyhedrons, which are different types of shapes. The one on the left in the lower left-hand corner, that of course is a pyramid. The one in the middle is a what? This one down here, that's right, it's a cube. A cube is kind of like a square in 3 dimensions. And this one is actually, I think, octagonal. It's also a regular polyhedron. It's also a regular, but I think that's octagonal. I think that's got, I don't know, 8 sides, I believe. How many sides does it have? 1, 2, 3, 4, 5. So yeah, I believe it's 8 sides altogether if you look at that. Yes, so I think that's actually an octahedron, I think it's called. Because it's got 8 sides and it's a polyhedron, which is a regular 3-dimensional object. Okay. Then there are some other 3-dimensional objects that are not polyhedrons. There are... these are polyhedrons, which means they're regular, which means they're all the same in all directions. The cube and this over here, they're all pretty much constant throughout. How about things like this? These are also volumetric. These are also volume-based shapes. These are also dimensional shapes. Look at the cylinder. What does the cylinder remind you of? The right circular cylinder. Here has essentially a circle with a height. A circle is a 2-dimensional object, so if you take the circle and you kind of stretch it out and give it some height, now it becomes a cylinder. You've got an oblique cylinder, which is essentially a cylinder that instead of being straight up and down, it's an angle. Kind of like, imagine if you had a can in your oatmeal container or your pop can, and instead of being straight up, it was like the Leaning Tower of Pisa, and you had your can was kind of leaning over to the side. Then you've got a cone. Again, these are all things that have to do with that have circles in them. A cone is similar to a cylinder, except that instead of the circle being constant as it goes up all the way to the top, the circle fades to an individual point all the way on the top. And then finally we've got the sphere, and the sphere is a ball. A sphere is not a circle. Do you ever say, throw me the circle? probably not. I mean, you might, but that would not be appropriate. It would be throw me the sphere. That's right. Did anybody? I see you actually read it. Did anybody else read the link I put up there? It's a very interesting story. I was actually reading it. It's actually better than the original for our purposes. Now, the original had more social commentary and more commentary on it was the original was kind of a cross between a mathematical story and also a political satire. So this one was not quite as much, but this one had a lot of discussion of shapes and geometry, etc., etc. So the sphere is like the circle from Spaceland, although honestly, if I were taking a circle from Flatland and putting it into Spaceland, I would almost make it more like a cylinder than a sphere. Because if you take a circle and you just add a dimension to it, you just add a height to it, you're not really getting a sphere. If you just take a circle and you add height to it, really what you're getting is a cylinder. You're just kind of stretching it out. Because the sphere doesn't keep that constant circular property to it throughout. It doesn't keep the same dimensions throughout. Okay, but that's what a sphere is. And finally, before we get to some practice questions, to go over and this is something that's also discussed in the book, something called a dimensional analysis. A dimensional analysis is the idea of converting units to what those units represent. It's a section in the book, and I think it's important. It might be self-explanatory. You might know this intuitively, but I still think it pays to go over a little bit. When you're looking at a map, the map might be drawn to scale, or the map might be not drawn to scale. Is a good map drawn to scale? The answer, of course, is yes. Without it being drawn to scale, it's much less useful. A map that's drawn to scale means that the distances on the map are obviously not the exact same distances they are in real life. I mean, this is a piece of paper, and that's a real thing, but they're proportional. If 1 inch on the map equals 10 miles in the land, in real life, well, then that is a proportional map. That is drawn to scale. A good map has to be drawn to scale because you can look across a map. You can look across a good map and say, by the way, for those of you who are only used to using Google Maps, or a map is a piece of paper. It's like one of these things that they cut down a tree and they take a thin slice of the bark of the tree and they draw places on it and draw little lines that represent roads. Anybody know what I'm talking about? Yeah, I mean, I haven't either used a map in the last, probably 5 years or so. But back in the old days when people used to use maps, that's what actually a map was. Right, exactly. It's if you open up your glove compartment, you may actually find one. It might be from, 1987, but right, okay. So I actually still sometimes look at maps, but not when I'm driving. When I'm driving, I just use my phone. Sometimes if I'm at home and I'm curious about going places, sometimes I'll take out a map, but not really. Maps are now. It used to be you'd actually use a map for utility. You'd actually use a map because you needed to find out how to get there. Now you just use maps to kind of, I don't know, for fun. Anyway, so if 1 inch equals a mile, well, then that is a way to look in terms of proportion. You'd have to look at it in terms of proportion. Let's say in this example over here that I have in the slide. 1 inch on a map equals 20 miles. How many miles are in 2 feet? So first thing you got to do is convert the feet into inches, because you were told that 1 inch equals 20 miles. So 2 feet is 24 inches. 1 foot is 12 inches. And so 24 inches altogether, because 1 inch is 20 miles, 24 inches altogether is 480 miles. So, if I told you that, let's say, 3 inches equals 60 miles, and then I told you how many miles is in 12 inches, well, I guess there are 2 ways you can do this. You can figure out that 60 divided by 3 is 20 and then multiply 12 by 20. Or what you can do is use a proportion. And a proportion is simply a fraction that you have 3 is to 12 as 60 is to x. Essentially because of the fact that they represent the same thing, they represent the same proportion. When you have something like this, you do what's called a cross multiplication. This is a basic algebraic procedure. You do the 3 times x, which is 3x, and on the other side, you do the 60 times 12, which is 720. And then, to isolate the x, you divide each side by 3, and 720 divided by 3 is, what's that, 240? I think so, yeah. Okay. And there's your answer. So this is really simply a matter, in order to scale dimensions, what you really need to do is increase the size proportionally. You ever see Shark Tank? The show where they talk about businesses and entrepreneurs and whatnot? One of the things they always ask, especially Kevin, he says, how are you going to scale this business? Well, what does he mean? What he means is, how are you going to dramatically increase it proportionally? Well, you know, you're spending $900,000 and making $1 million this year. So how are you going to scale that to the point where instead of spending $900,000 and making $1 million, you're going to spend $90 million and make $100 million? You may be working on the same proportions, but you're going to make a lot more money because the overall amount is much higher. And then we move to what may be the most interesting of all shapes, and that is the circle. The circle, which I cannot draw very well. Let me draw a bigger one here. Oh man, this is a lousy circle. Alright, I am not good at... Okay, I see, the thing is, not only am I bad at drawing in general, but drawing with this tablet makes it even harder. Alright, this is going to have to do for a circle, or you can use the one that's on the slide. Okay. When we talk about distances, I didn't even mention this before, but let's say we're talking about the regular quadrilateral. Let's say this is a rectangle. The perimeter means the total distance around the rectangle. So ABCD, the distance from here to here to here to here, that would be the perimeter. The area, as we discussed, is the entire amount on the inside. Now, for a circle, the perimeter is called the circumference, as a special name. And there are a few interesting properties of a circle. The distance from the center of the circle to the edge, called a radius. That's what a radius of a circle is, just the distance from the center to the edge. The double that from one side to the other side through the center is called the diameter. Diameter is always twice as much as the radius, and the circumference is the around the amount on the edge of the circle. And that is where we get the concept that you're going to become very familiar with as we move along, called pi. We're all familiar with pi, and I'm not talking about or pizza pie or a peach cobbler or anything like that. It's approximately 3.14, 3.14159, etc. It's an irrational number. It goes on forever, but it's approximately 3.14. But the number pi is a constant. It's a number. It's always the same number, approximately 3.14. And what pi is the ratio of a circumference of the circle to its diameter. If you divide the circumference of the circle by its diameter, you will get pi. Let's say this is the center of our circle, and we've got a line that goes through the center to the other side. If this were a real-life circle, you were going around the fountain or whatever, if you walked the blue line and then you walked the red line, the blue line would be 3.14 times as long as the red line. That is, it's a special number. It's a number that was figured out by the Greeks, I don't know, 2,000 years ago or whatever it is. And that's really what pi is. That's what pi... Yeah, the diameter of the circle. It's 3.14 times the diameter. The circumference is 3.14 times the diameter of the circle. So, you know, we didn't really get started on formulas yet, but the circumference of a circle is pi times the diameter of the circle, or 2 pi r, 2 pi times the radius of the circle. And the reason is they're the same thing. Think about it. The diameter is twice as much as the radius. So saying pi times the diameter and 2 pi times the radius is the exact same thing. All right. Let us see if we have a chance to go over one or two of the homeworks here. Let's see, how do we want to do this? Oh, I'm sorry. Yeah, it should be the diameter. I'm going to put up the homework. And you know, let me put up the whiteboard here so that I can write over here in the lower left-hand corner of the board. All right, and we had a request before to go over number 2. Now, number 2, I don't necessarily want to go over it, but I want to just kind of simplify it a little bit, and then we'll look at number 6. Now, number 2 is one of those things that it's not very difficult once you figure out an approach. A landscaper is working on plans for a residential yard. Clients want a privacy hedge planted on 3 sides of the rectangular backyard. This would actually be a little harder if they didn't actually draw it for you. Then you'd have to draw it yourself. So the plant for the hedge, the plant selected for the hedge spans 5 feet when mature. If the backyard is 50 deep and 80 long, there is to be a plant, and there is to be a plant at the corner of the hedge. How many hedge plants are required? It means you're going to have one over here and one over here, and then you're going to have plants all across. Now, how are we going to how are we going to focus on this? What's the first thing we're going to think about over here? Well, each side is going to take up 5 feet for each hedge. So, I mean, if you really think about it, it's not that difficult. You just have to figure out how many plants are going to be necessary for each 50-foot side, and how many plants are going to be necessary for the 80-foot side. You know, once you figure it out, taking into account the fact that you're putting one in each corner, the answer will be relatively easy to figure out. Let's take a look at number 6. Number 6, answer the following questions in the given prism. Name the bases of the prism, the lateral faces, which means the faces going upwards, the faces hidden from view, the edges, and the type of prism. Well, type we actually discussed. It's on the slides, I believe. Let me just bring the slide back up for a second. I think it actually tells you what this is. It's certainly a triangular prism. You may be able to be a little bit more, but I think that's fine. Okay, the bases of prism. What does a base mean? Generally speaking, what is a base? A base is the bottom, that's right. Now, a base, so over here, I mean, I think it should be fairly self-explanatory what the bottom are. What shape is the bottom, by the way? What shape is the base? The base is not a triangle. I don't think the base is a triangle. Think about what is it sitting on? It's a rectangle, that's right. It's a rectangle. And what's the name of that rectangle? What's the name of the rectangle that it's sitting on? How would you put it? A, B, D, F. Yeah. See that? I mean, of course, the reason why the lines in the back of it is because, like the ones that are kind of hidden from view, if the front was solid. But yeah, it's sitting on a rectangle that's A, B, D, F. I'm sorry, A, B, F, D. or ADFB, or BFDA, any way you call it. The lateral faces means this side and the back side. The edges are what shape are the lateral faces, and what shape are the edges? The lateral faces are going to be rectangles, right? The lateral face, for example, this over here, I guess BCEF is one, and the other one in the back. And the sides, the edges, are going to be triangles, of course. Okay. Now I want to try either 7 or 8. I'll do one of them with you, and then the other one you can do yourself, because I want to see how I would go about doing this. Let's see number 7. The bearing of a line segment is the acute angle that the line segment makes with the north-south line. I'm going to use Microsoft Paint for this when we get there. Okay, if a line bearing PQ is north 70 degrees east, what that means, north 70 degrees east, is looking due north if the thing goes 70 degrees eastward. Now what I did was, what I would do in something like this, first of all, I'd use a protractor. You don't need one. I mean, you can imagine it, but if I were using a protractor, let's find an online protractor that we can use. Okay, something like this. So let's find a protractor. All right. Let's do a full 360-degree protractor so that we can, because we're gonna need 2 of them. Okay. Protractor is something like this. All right, so let's pick this up over here, and let's put this in our Microsoft Paint. Sorry, just give me a sec. If I had it physically, it would be a little easier, but I don't, so we're going to have to use Paint. Okay. Alright, let's make this a little smaller so we can actually see it. Alright, you know what? I'm going to have to zoom out. Okay, there we go. Alright, let's use this. And let's get the question. Okay, so this is the question. We'll put the question over. Make the question a little smaller. Now you can't see it. All right. This is not working. All right, we'll put it over here. I think there still should be enough room over here, even though it interferes a little bit. Okay. Can I show the email I sent you? It's a good point. Let's do it though. I mean, maybe I can show it afterwards, but let's do it. I have an idea. Let me make this a little bigger so that you can see it a little bit better. Can everybody see the Microsoft Paint over here that I have? I just tried to make it a little bit bigger, so hopefully that'll help. All right. The bearing of a line segment PQ is that it makes with the north-south line. Okay. If the bearing PQ is north 70 degrees east. So let's make a segment. Let's make a line, and this line is gonna start in the middle. We'll start it right over here somewhere, and we will, instead of in north 70 degrees east means you're facing north and moving over 70 degrees to the east. So north is upwards and east is to the right on a general compass. So instead of going up, I'm going to start up, but I'm going to move it over 70 degrees to the right. So from 360, 70 degrees drops to 290. Actually, you know what? This doesn't really start in the middle. Let me try to estimate start in the middle. Okay, I think that looks a little better. That's more to the middle. Okay, so it starts north, and I'm going to extend it 70 degrees. See how I did that? Because it started straight up, and then I moved it 70 over, which means 360 to 290, which is 70 degrees. And this I'm going to call line PQ. We'll call this P, and this Q. Okay. Okay, then the next one, the bearing of PR is south 32 degrees west. So again, I'm going to start at the same place. I'm going to start down, straight down at 180, although it's not perfect, but it's close enough. And it's going to move it over 32 degrees. Now, to move it over 32 degrees from 180, it's going to have to be here to the 148 because I moved it over 32 degrees. So this is R. So this is line PR. So what they ask over here is, what is the measure of obtuse angle QPR? QPR is, of course, this angle. So how would we figure this out? Anybody want to help me figure this out? Well, how many degrees is it altogether from this line to that line down there? How would we go about counting that? Well, first, let's use a line. Let's use this line. So we start over here. Now, to get to flat is 20 more degrees, right? I mean, you could draw those lines, or you could just count it. From here to here is 20 more degrees, because here's 290, goes to 270, it goes flat. Remember, the whole quarter of a circle is 90, so from here to here was 70, so from here to here has to be another 20. Now, to get from here all the way down here to straight down has to be another 90. So we've got 20 plus 90, which is already 110. Then we went another 32 degrees. And 110 plus 32 is 142 degrees. See how I counted that? I didn't count it by actually measuring it or anything like that. I just look at where is it headed. It's headed toward 20 degrees north of east, or 70 degrees east of north. So 20 to get it flat, another 90 to get it another quarter of the circle, it's 110, and then we needed to make it 32 degrees further over this way. Altogether, that's 142 degrees. Let me look for that email that I was referring to. All right, where is it? Okay. All right, anyway. So this is, all right, anyway, where's my, all right, where's the email? There we go. All right, can everybody see my, see the email over here? So this is the way I did it with, this is the way I did it, you know, just the first, well, really, it's really the same thing. I just used something that was a little better because it had this thing in the middle to help us through, and basically drew these same two lines. It's really the same thing as what we just did. So if you understood what we just did, then you probably understand this as well. Okay, so with that in mind, it's a little after the top of the hour, so I am going to wrap it up for today. If anybody has any questions, please feel free to stick around. I encourage everybody to come back on Monday when we have Class 3, and for those of you who are not here and listening on the recording, I encourage everybody to please come on Monday when we have Class 3. So have a fantastic evening, everybody. Encourage everybody to come back on Monday when we have Class 3, and for those of you who are not here and listening on the recording, I encourage everybody to please come on Monday when we have Class 3. So have a fantastic evening, everybody.